Next topic is Euclidean algorithm. We know that it is easy to find GCD of small numbers by direct method. For example, if we want to find GCD of 12 and 30, then what will we do? We write the divisors of 12, 1, 2, 3, 4, 6 and 12, and the divisors of 30 are 1, 2, 3, 5, 6, 10, 15 and 30, and the common divisors of 12 and 30 are 1, 2, 3 and 6, and the greatest among these common divisors is 6. So 6 is the answer. So this is the direct method by which we can easily find GCD. But what we cannot use this method for larger numbers, like we want to find GCD of 1, 3, 4, 9 and 2, 5, 6, 4. So this method is not applicable here. Now for this we use Euclidean algorithm, which gives us a new method to find GCD. What is that? It's actually the repetition of division algorithm. Let's try this method. We want to find GCD of A and B. So by division algorithm, we divide A by B. We get quotient and remainder. A is equals to Q1B plus R1, with R1 lie between 0 and B. If R1 is 0, what this imply? This equation imply A is equal to Q1B, which further means B divides A. Now if B divides A, then GCD of A and B is B. So we are done in that case. But if R1 is not 0, we divide B by R1 to get B is equal to Q2 R1 plus, and R2 lie between 0 and R1. If R2 is 0, we are done. If not, we again divide R1 by R2. R1 equals Q3 R2 plus R3, where R3 lie between 0 and R2. So we keep on doing this. So this process will over when zero remainder occurs, and that certainly occurs because we are having a strictly decreasing sequence of remainders which is greater than equal to 0. So certainly after B steps we get 0 remainder. The given system of equations become A is equal to Q1B plus R1 with R1 less than B. B is equal to Q2 R1 plus R2. R2 lie between this and R1. R1 is equal to Q3 R2 plus R3. R3 less than R2. And after n plus 1 steps, we have Rn minus 2 equals Qn Rn minus 1 plus Rn, with Rn greater than 0 less than Rn minus 1, and at last Rn minus 1 is Qn plus 1 Rn plus 0 remainder. Now here we claim that GCD of AB is Rn. Now to prove this, we need this lemma. Let D is GCD of AB, and by definition of GCD, D divides A, D divides B, D divides A minus QB, which imply D divides R. So we get D is a common divisor of B and R. If there is another common divisor of B and R, C divides B and C divides R, then C divides their linear combination, that is QB plus R, which implies C divides A. Now combining C divides A and C divides B imply C divides D. So C has to be less than equal to D. Means D is the GCD of B and R. So we started with D is GCD of A and B, and we proved D is also GCD of B and R. So using this, we apply this result here, that GCD of A, B equals GCD of B R1, which equals GCD of R1 R2, which equals GCD of R2 R3, so on, equals GCD of Rn minus 1 Rn, equals GCD of Rn 0, which is Rn. So hence GCD of AB is Rn. Required answer. Now we have definition of LCM, least common multiple. So which is a common multiple, and if there is another common multiple, then M has to be less than equal to C. So here important thing is least common multiple is always positive, and it has to satisfy these two properties. And with this, GCD of two numbers multiplied with their LCM equals product of numbers. And if GCD of two numbers is 1, when we put GCD 1, what we get? LCM is equal to product of two numbers. So with this knowledge, we have problem set 2.4, and the first question is to find xy using Euclidean algorithm. So with that, we start with finding GCD of 56 and 72 by Euclidean algorithm. When we divide 72 by 56, quotient is 1, remainder is 16. Now we divide 56 by 16, quotient is 3, remainder is 8. Now we divide 16 by 8, quotient is 2 and remainder is 0. So GCD here is last non-zero remainder, that is 8. So GCD of 56 and 72 is 8. Now we express 8 as the linear combination of 56 and 72. So for that, from second equation, 8 equals 56 minus 3 times 16. And now we eliminate 16 using first equation. So 56 minus 3 times 72 minus 1 times 56. So combining the same terms, 56 3 times 72 plus 3 times 56. So 3 plus 1, 4 times 56, 3 times 72. So we get this. So when we compare with this given equation, so x is 4 and y is minus 3. Desired answer. Find x and y using Euclidean algorithm for GCD of 24, 138, 24x plus 138y. So first we find this GCD. For that purpose, we divide 138 by 24. Quotient is 5, remainder is 18. We divide 24 by 18. We get 1 quotient, 6 remainder. Now we divide 18 by 6. Quotient is 3 and remainder is 0. So last non-zero remainder is 6. So GCD of 24 and 138 is 6. Now using the same method, we express 6 as, from this equation, 224 minus 1 times 18, and putting value of 18 from first equation, 24 minus 1 times 138, 5 times 24. So further solving, 24 1 times 138 minus minus plus 5 times 24. So combining the coefficient of 24, that is 6 times 24, 1 times 138. So we get GCD equals 6 into 24, 1 into 138. So comparing with the given equation, x is 6, y is minus 1. Assuming GCD of A and B is 1, prove that GCD of this is 1 or 2. So we let D is GCD of A plus B and A minus B. So by definition of GCD, D divides A plus B, D divides A minus B, and also D divides their linear combination, A plus B times X, A minus B times Y. So now we choose value of X and Y such that we are left with 2A and 2B. For that purpose, first we put X is equal to 1, Y equals to 1. So we get D divides A plus B plus A minus B. So which cancels and gives D divides 2A. Now for X is equal to 1 minus 1, we get D divides A plus B minus A plus B. So A cancels, we get here we are that D divides A, D divides 2B, which imply D divides GCD of 2A and 2B. And we know that GCD of KA and KB is K times GCD of AB. So 2 may be written outside. This implies D divides 2 times GCD of AB, given that is 1. So D divides 2, which further gives D is 1 or 2. Answer. So in the next question, so with similar steps we will do this. So we start with, let D is GCD of 2A plus B, A plus 2B. So by definition of GCD, D divides 2A plus B and D divides A plus 2B. So D divide their linear combination, 2A plus B times X, A plus 2B times Y. Now we choose value of X and Y such that we are left with D divides 3A and D divides 3B. For that purpose, first we choose X is equal to 2, Y equals to minus 1, and we get this is 4A plus 2B minus A minus 2B. 2B cancels, D divides 3A. And in the second case, we choose X is equal to minus 1, Y equals to 2. So D divides minus 2A minus B plus 2A 4B. So 2A 2A cancel, we are left with D divides 3. So from both the cases what we have, D divides 3A, D divides 3B, imply D divide the GCD of 3A and 3B, which means D divides 3 times GCD of AB. So using same result, that K can be written outside, so 3 may be written outside. So which further imply D divides 3 because GCD of A and B is 1. So which means D is 1 or 3. Answer. Positive integer a and b show that if GCD of ab is 1, their GCD of their nth power is 1. We know the smallest positive divisor of any integer is prime. And second property, that if p divide a power n imply p divides a. So using these two properties, let d is GCD of a power n b power n, which means d divides a power n and d divides p power n. Now using first property, there exists p such that p divides d. And now combining p divides d and p divides a power n imply p divides a power n, and using this p divides a. Now again combining that p divides d and d divides b power n imply p divides b power n, using the property of prime p divides b. Now further, p divides a, p divides b, p divides GCD of a and b. What is that? 1. So which is a contradiction, because p is prime, so p has to be strictly greater than 1. P cannot divide 1. So our supposition is wrong, that this GCD cannot be 1. So means GCD of a power n and b power n is 1. Answer. Second part, a power n divides b power n imply a divides b. So we start with, let d is GCD of ab, means d divide a, d divide b. So using definition of divisibility, there exist integers r and s such that a is equal to dr, b is equal to ds. And also we know that r and s are relatively prime integers, and using part a, this means r power n and s power n has also GCD 1. Now to prove the desired result, what we prove? R is 1. Given a power n divides b power n, putting the value of a and b here, a is dr, d power n r power n divides d power n s power n. As d is not 0, so it can be cancelled. So we are left with r power n divides s power n. So which means GCD of r power n and s power n is r power n. But we know that this is 1. So that r power n is 1 imply r is 1. Now put r is equal to 1 in this relation. So what we get? A is equal to d. Means a divides b. Answer. If GCD of a and b is 1, prove that GCD of a plus b and ab is 1. To prove this, we again start with, let this GCD is not 1, it is d. Let it is d. So by definition, d divides a plus b, d divides ab, and d divides their linear combination ab times x, ab times y. Now we choose values of x and y so that we get d divide a square and d divide b square. So let's take first for x is equal to a, and y equals to minus 1. So we get d divides a square plus ab minus ab, which imply d divides a square. Now for x is equal to b, y equal to minus 1. So we get d divides ab plus b square minus ab. So again we get d divide b square. So as in the previous manner, what we have, d divide a square and d divide b square. So we know there exists a prime number such that which divides d. Now p divides d and d divide a square imply p divide a square, and further we know then p will divide a. Similarly, from the second, p divides d, d divide b square imply p divide b square, which is p divides b. So combining these two, p divide a and p divide b imply p divide GCD of ab, which is 1. So we get a contradiction that p will not divide 1. So which means supposition is wrong. Desired answer. Now, next question. Prove that GCD of two positive integers divide their LCM. So let a and b be two positive integers, and further let d is GCD of AB and L is LCM of AB. So using the definitions of GCD and LCM, what we get? D divides A, D divides B. And from that definition of LCM, we get A divides L and B divides L. Now, look at this. D divides A divides L imply D divides L. From second part, D divides B and B divides L imply D divides L. So we get the desired result that GCD of two numbers divides their LCM. Hence the answer. So that's it.